Hey guys, so for today's Wednesday e-learning day, we're going to be starting topic 9. So for topic 9, we're going to be looking at right triangles. And for 9.1, we're going to talk about similarity that happens between right triangles as well as something called geometric mean. So I have this lesson split up into two parts. The first part, geometric mean, will be pretty short, and then we're going to look at right triangle similarity. So geometric mean is something we can look at actually as a proportion. So geometric mean is a number, and it says that given two numbers, A and B are just any generic numbers, the geometric mean is the positive number x that satisfies the proportion A, so one of our given numbers, over x equals x over our other given number, which is b. And x is going to be like our geometric mean value. So if you take a look, this is a proportion. X is diagonal from itself. So let's solve this proportion and let's kind of see what happens here. So we're going to solve the proportion for x. Remember, when you solve a proportion, you cross multiply. Oh, didn't mean to erase. It should be an A on top, X on the bottom. Okay, so when we solve our proportion, we cross multiply. So x times x is going to give you x squared. And then A times B is just going to be AB, or A times B. And then something you're going to have to remember from algebra now is to solve for x, you have to get rid of that squared. And the opposite of squaring something is square rooting. So we are going to square root both sides. We don't know what A and B are, so we would just write our final answer as x, our geometric mean, equals the square root of whatever A times B is. And what's going to happen is that A and B are going to be numbers, so we are going to have to reduce some radicals here. Sometimes they're going to be perfect squares, like numbers like 4, 9, 16, 25. Sometimes they won't be. So we did reduce radicals back in semester 1 when we talked about the distance formula. If you need a refresher on reducing radicals, please watch the video I posted in today's module about reducing radicals. We will have to reduce radicals throughout this chapter, so it's going to be a skill we continue to review. So please, 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 if that's something you don't remember how to do, watch the video I posted. So we're going to practice finding the geometric mean between some sets of numbers here. So first we're going to look at 12 and 8. So what's going to happen here is when we set up our proportion, our 12 and our 8 are going to be diagonal, and then our x, our geometric mean that we solve for, is going to be diagonal. So if I set this up, so like one of my numbers here is 12. So if I maybe did 12 over my geometric mean, which I don't know, x, equals x over 8. So you want to make sure your x's are diagonal and your given numbers are diagonal. Now this is not the only way you could set this up. If you prefer, you could do x over 12 equals 8 over x. You're going to get the same thing, so it doesn't matter. So let's go through and solve. So remember, multiply diagonally. X times x is x squared. 8 times 12 is 96. Now we need to get rid of our square, so we are going to square root both sides. Now 96 is not a perfect square. So you need to think of numbers that divide into 96, and you want to think of specifically perfect squares that divide into 96. So for example, perfect squares are like 4, 9, 16, 25, and so on. So you can always in your calculator see, okay, well, does 4 go into 96? Does 16 go into 96? Does 25 go into 96? Does 36 go into 96? And you always want to pick the biggest one. So the biggest perfect square that goes into 96 is actually 16. So how I'm going to split this up as x equals, and instead of writing this as a 96, I'm going to change this into 16 times 6, because 16 times 6 is 96. Excuse me, and 16 is a perfect square. Then what I'm going to do is reduce this. The square root of 16 is 4. So the 4 comes out of the radical and the 6 stays behind. So my geometric mean is 4 root 6. And you will have to write these as radicals, not as decimals. Again, if that does not make sense to you, please watch the reducing radical video that I posted in today's module. All right, let's do part B. Here we have the numbers 5 and 45. So we're going to, again, place those diagonally. So this would be 5 over x equals x over 45. We're going to multiply. X times x is x squared. 5 times 45 is 225. Now to get rid of the square, we are going to square root both sides. And if you try to do the square root of 225 in your calculator, this actually is a perfect square. The square root of 225 is 15, and that's because 15 times 15 is 225. So that one ends up being a nice whole number. And then the next one, we have 17 and 36. So we're going to put our 17 and our 36 diagonally. So 17 over x equals x over 36. We're going to multiply. X times x is x squared. 17 times 36 is a big number. 17 times 36 is 612. Now, something you might notice about these numbers, 36, right here, 36 is already a perfect square. And 17 is actually prime. You can't split up 17 except 17 and 1. So if I take these and multiply them, I'm going to get 612, which is a huge number, and that's going to be really hard to reduce. But what I notice here is that one of my two numbers is already a perfect square. So I'm actually not going to bother multiplying them together. I'm just going to say that I'm just going to leave this as 36 times 17. Because again, I see 36 is already a perfect square. I'm going to square root both sides. And then when I do that, I don't have to multiply and then just re-reduce again, because I know the square root of 36 is 6. So that comes out, and the 17 stays underneath. Okay, if you're confused about the reducing radicals, again, watch that video. More focus on making sure you understand the process for finding the geometric mean. Okay, if you're a little confused with the reducing, we can work on that. And then example 2 says the geometric mean of a number and a fourth of that number is 8. What are the two numbers? So the geometric mean of a number, we don't know that number, and a fourth of that number is 8. So this time, our geometric mean, we know it. It's 8. We don't know the other two numbers. So if I don't know something, remember in math, we assign a variable to it. So the geometric mean of a number, I don't know what it is, I'm going to call it x. And a fourth of that number, I'm going to call that 1/4 x, or if you prefer 0.25x, it doesn't matter. Okay. My assumption is that we'll probably prefer a decimal, so I'll change that into 0.25x. That's a fourth of x. And its geometric mean is 8. So we want to put our x and our 2.5x diagonal, and then the geometric mean is 8, so 8 and 8 will also be diagonal. Okay. So here I don't know my two numbers. My one number is x, and then my other number is 0.25x. So I'm going to put those diagonal. Then my geometric mean is 8, so that's like up above where we had those x's, right, that's where our 8's going to go, because that is our geometric mean this time. So I'm going to put an 8 and an 8. And now I'm going to cross multiply. It doesn't matter what order you multiply in. I always like to start with my variables, though. So x times 0.25x is going to give me 0.25x squared equals, and then 8 times 8 is 64. Now you're just solving for x, so we need to get x all by itself. So I'm going to divide both sides by 0.25. So 64 divided by 0.25 is going to give me 256. So now I have x squared equals 256. Now I need to get rid of my square, so I'm going to square root. And in your calculators, the square root of 225, you should get 16. So it says, what are the two numbers? Well, it says the geometric mean of a number, x, which we just found to be 16, and a fourth of that number. Well, a fourth of 16 is 4. So what are the two numbers? We would say 16 and 4. Okay, that one's a little trickier with the word problem stuff. But again, just make sure you understand this general process up here for finding your geometric mean. All right, so that's all for this part of the video, and then in the next video, we're going to talk about right triangle similarity.